All right, in this video, we're gonna see if the series circuit rules actually hold true. So I have a circuit, I have a battery. So we have the plus and the minus. The plus is the big bar, minus is the small bar. I have two resistors. I only have one way for the current. So if I follow my finger around, if I do electron flow coming out of the minus, if I follow my finger around, all the current, there's only one path, has to go through this resistor. All the current have to go through that resistor back to the battery. So in this circuit, let's say I know that my battery is 6.37 volts. I have 221 volts for this resistor. I have 327 ohms for this resistor. So to solve it, I draw a circle around each one of my resistors and the battery. Within each one of them, I'm going to write V, I, R, V, I, R, voltage, current, resistance. V, I, R. Then I'm going to write down what I know. In each circle, what do I know? So for the battery, I know I have I have 6.37 volts. That's all I know for the battery. In this resistor, all I know is my resistance, 327 ohms. On this resistor, all I know is the resistance, 221 ohms. So in any of these, in any one of my circles, if I know 2 out of 3, I can use Ohm's law to find the third. So on this one, I know 1 out of 3 my voltage, 1 out of 3 my resistance, 1 out of 3 my resistance. So to find my values, I got to use one of my series rules. So in my series circuit, rule number 1, all the currents are the same. And scientifically, we write that as I total equals IR1 equals IR2. But really what it means is the current coming out of the battery is the same as the current going through this resistor, same as the current going through that resistor. Since we don't know any of the currents, that doesn't help us. Second rule, my total voltage is the sum of the voltage across each resistor. So basically, my total voltage, 6.37, is going to split up between these two resistors. So the voltage here and the voltage here is going to add up to 6.37. Since I don't know the voltages on these two, that doesn't help me. An unknown and an unknown adds up to 6.37, not enough information to do anything. So my third rule, my total resistance is the sum of all the resistors in the circuits. So basically, on this guy, my total resistance by the battery is the sum of this guy plus this guy. So basically down here, my R total is R1 plus R2. So it's going to be 221 plus 327 ohms. So let me get a calculator out. So I go on this guy, 221 plus 327, it's going to be 548 ohms. Okay, so now I know 2 out of 3, I can find the third. So I know my voltage and my resistance, I need to find the current. If we look at Ohm's law, current I, voltage divided by resistance. So I can go in, my current, voltage divided by resistance, 6.37 divided by 548. So I go 6.37 divided by 548. It's 0.0116 amps, same as 11.6 milliamps. Okay, so now I know all three things about my battery. I know I have 6.37 volts in the battery. 11.6 milliamps should be coming out of the battery. My total resistance that the battery sees for the entire circuit is 548. I only know 1 out of 3. I only know 1 out of 3. So now I got to go back to my series circuit rules. All the currents are the same in the first rule. So if I have 11.6 milliamps going out this way, I got to have 11.6 milliamp, which again, same as 0.0116 amps. You know, just basically divide it. When you see milli, divide by 1,000. Okay, so up here I have 11.6 milliamps. Right here, how much would I have? 11.6. What about right there? 11.6. There's only one way for the current. And remember, current is just the number of electrons flowing by a certain point every, whatever time that you have. So if I go in, all the electron that comes out here have to pass through this resistor, have to pass through this resistor, have to go back into the battery. So current, same everywhere. So now I know 2 out of 3. I know my current and I know my resistance. I can find my voltage. So voltage, I times R. So I have I times R. So I have 0.0116 times 327. So times 327 is 3.8. 3.8 volts. So if I go up, grab a sip of my coffee here. If I go up to this guy, I have 0.0116 times 221, or 2.56. 56 volts. So now I know everything about my circuit. I have 3 out of 3 everywhere. And just to double check things, right? What if I add my 2 voltages? So remember, my total voltage is the sum of the voltages across each resistor. So if I go on this guy, I'll go my total voltage equals VR1, voltage across resistor 1, plus VR2, voltage across resistor 2. So that would be 2.56 plus 3.8. Take my calculator, plus 3.8, bam, 6.36. So 3.36, 3.37, very, very close. So let's see, next step, does all this actually hold true on a real circuit? Is everything that we are teaching you guys, does that actually make sense? And remember, a series circuit is made to control typically how much current or voltage goes into a component. You buy like a really expensive CPU, whatever chip, a certain amount of voltage or current has to go into. You can control that with a external resistor. So for example, this might be the resistance of your CPU or your headlamp, whatever. If I want to ensure a certain amount of current or voltage goes into that, I put another resistor in series with that. So anytime we want to control something in a circuit, typically it's a series circuit, part of a series circuit. So now let's go down and see if this actually works. Let me flip it upside down. Bam. So I have in my circuit, I have a battery, I have the first resistor, I have the second resistor. So let's see if all my values hold true. So I have a multimeter. I see the little ohm system, old ohm symbol. I can measure my resistances. So see how there's a K by it says 2K right there. So all my answers are going to be in kilos. So if I measure this guy, whoa, hold on. There we go. So 221 ohms. So 0.222 kilos, 221 ohms. If I go into this guy, I have 326 ohms, 0.325 kilo ohms, or about 325 ohms. So now if I go in and I hook these two up together, so I put a wire in between them, bam, bam, I'm going to put my meter on top of it. So now I basically have like a series circuit. If I put my probes across both of them, between both of them, I measure 546. We calculated in hours, we calculated 548. So we are within 2 ohms of that, incredibly accurate. So now I'm going to hook it up to the battery. So I have the plus terminal, the minus terminal. I always use a red wire for the plus terminal, just like if you open your car hood, you see that the positive is red and the negative is black. So it helps us be safe. It helps us to figure out what's positive and negative, and so forth, so we can be safe and hook up stuff correctly. So now I go in, I have current flowing. There's only one way. If I use electron flow, all of my current comes out the negative, goes through this resistor, goes through that resistor, and back into the positive. So electron flow right down. So let's measure our voltages. Okay, so I put it on voltage right here. The maximum I'm going to see is 20, so it's on voltage. So I measure my battery. 6.43 volts. I think in our example, we had 6.37. So fairly close to our example, a little bit off. Check it out. If I reverse my probes, right? So I put the positive meter probe on the minus side, this guy, I get the same result, but I just have a negative. So the voltage is the same, it's just telling me it's flowing in the opposite direction. Okay, so now I got to see how much voltage across each resistor. So I have on this guy, I have 3.82. We calculated 3.79 in our example, so very close. On this guy, I have 2.59. We calculated 2.57, so incredibly close. And the two voltages add up here. So we see that the voltage in the battery split up between these two. About 3.8 went here, about 2.57 went right here. So far, the resistance rule held true, the voltage rule held true. Now let's look at the current. So I put it on milliamp current A, and it's going to be in milli. The 20 means that's a maximum I would see. So if I look at how much current comes out of the battery, 11.6 milliamps. See how that's a minus? That just means the direction is opposite of the way I had the probes. Now it'll show 11.6. So we calculate 11.6 milliamps. We have 11.61 milliamps flowing right now. So our calculations were exactly true. Okay, what about right here? How much current do I have? I have 11.6, 11.59, or 11.6 milliamps. What? Exactly the same. What about on the other side of this resistor? I have 11.6 milliamps. What about over by this resistor? Make a break in the circuit. Current flows through my meter. I have 11.6 milliamps. So I have the same amount of current everywhere. What about flowing back into the battery? I have 11.6 milliamps. So all my currents in this were the same. So now you've seen that everything we calculated, I'm upside down. Everything that we calculated in the circuit was exactly true for what we measured. So these kind of very simple ways of calculating and solving a circuit works in real life. The calculations that you're doing is exactly what's happening in the real circuit. So the series circuit rules all held true. So hopefully that was enlightening to you to see that the calculations you do actually mean something. We can measure them exactly like they are. So typically what we do again is if we know how much current a certain component need, we can pick a value based on how much current or voltage that we need. We can calculate ahead of time what is going to keep that component safe and keep it from burning out.